Welcome back, Chemi 330 students. Today's example will cover Navier-Stokes and Cartesian coordinates. We're going to use the Navier-Stokes equations to analyze fluid flowing down an incline with the upper surface open to the atmosphere. Flow is in the x direction according to the coordinate system that we've defined, so we'll begin with the x component of the Navier-Stokes equations. Assuming that we're at steady state, the time derivative goes to 0. For fully developed flow, our x velocity doesn't change in the x direction. This assumption applies to both the first and second derivatives of the x velocity with respect to x. We also assume that velocity in the y direction is 0, and we can also assume that the z velocity is 0, or set this term equal to 0 because we're looking at a two-dimensional problem. This also eliminates the second derivative of the x velocity with respect to z. So we arrive at a simplified equation with two terms, which we can rearrange before we solve. And finally, since velocity only changes in the y direction and pressure in the x direction, we can make our partial derivatives into total derivatives. Now to solve, we'll define our boundary conditions. The first is the no-slip condition. This tells us that our x velocity at the surface of the incline, where y equals 0, is equal to 0. Our second boundary condition results from the fact that the normal viscous stress at the upper surface of the fluid must be 0. The other way to look at this is that there's nothing at the upper surface that can cause any change to the fluid velocity. This tells us that at y equal to h, our first derivative of the x velocity with respect to y is equal to 0. Before we solve our equation, there's one more simplification that we can make. We know that our modified pressure is equal to the applied pressure minus the effect of gravity. There is no applied pressure in this case. So dp dx is just equal to minus rho gx. And the x component of gravity is just equal to g sine theta. Substituting that result into our Navier-Stokes equation, we are now ready to solve. Our first integration with respect to y gives us this result with our first constant of integration. We can solve for this constant by applying our boundary condition for the air-fluid interface, which gives us that C1 is equal to minus rho g over mu sine theta h. We now perform a second integration with respect to y, which results in an equation for Vx with a second constant of integration C2. We now apply our no-slip boundary condition to determine C2. Evaluating for Vx equals 0 at y equals 0, we see that C2 is simply equal to 0. We now have an expression for Vx with both constants of integration known. We substitute 0 for C2 and our result for C1. We can then solve our expression for Vx, and by factoring out the coefficient rho g over mu sine theta y, we arrive at the expected velocity profile for fluid flowing down an inclined plane. Today's example is from Transport Modeling for Environmental Engineers and Scientists.